Okay, can you guys all see the screen?
Yep,
Okay.
I see the screen went up.
Okay, cool. All right, I'm gonna get started. So yeah, welcome to the last week of Techquitable. So today we're going to do a final reviews of all the topics that we have gone over. And these include topics from the technical side, which are listed here, as well as like the non-technical topics that we have also gone in the earlier parts of the program. So with the technical topics, here are the list of things that we're going to go over. So first, we're going to start out with time and space complexity. Then we're moving on to technical question approach. And then the rest are all the kind of the data structures that we have data structures or like algorithms that we have gone over. So yeah, so we'll kind of go one by one in the next 60 minutes. So bear with me, it will be a pretty time pressing task. So I might have to go fast on some of the topics. And then once we do that, we'll go over these non-technical topics, which are interview process, resume, and behavior questions. So first off, let's start with time and space complexity. So I hope all of you guys got to kind of practice answering these questions through your practices with your interviewers, or kind of think about it as you're writing out code. But here are the definitions, which is the time complexity measures the amount of time taken by an algorithm to run as a function of the length of the input. And space complexity is very similar, except this measures the amount of space in relation to the length of the input. All right, so what is the order of growth? Well, this describes how the time of execution depends on the length of the input. So there are three main notations here, which are big O notations, big omega notation, and big data notation. For most of the interview purpose, we focus on the big O notation, which describes like the asymptotic upper bound on how much time the function could run. And with regards to space, this can also be used to describe how much space it will take to run this function. And how do we calculate it? Well, in terms of mathematical terms, like what you do is you basically kind of calculate all these terms that could contribute to this like runtime or like the space requirement. And then what you do is you just ignore all the lower order terms and just focus on the largest terms here. So in this case, we have a bunch of these like constants getting multiplied to like these like variables and stuff. But in the end, we just focus on this like variable with like the highest order term, and that will be your big O notations. And this is how kind of big O grows in relation to different, I guess, like polynomial function. So at the bottom, this is like what we really want to achieve for in code, which is like constant time, which is honestly only takes like a one operation in computer to like execute it. Something that's a little faster is log n, which is basically allows you to kind of cut down the space or like the runtime by just like a logarithmic function. And log n is faster than O of n runtime, which is like this like a linear function that basically kind of scales constantly along with your input. And then there's also a bunch of others. Some of the notable ones is n log n, which we learned during this like lesson on sorting, that most of the sorting algorithm has the best runtime at O of n log n. There are some caveats that we haven't introduced, such as like bucket sort or radix sort that could have a runtime of linear time, but certain conditions have been met. So for the most part, we just assume that the runtime of these like sorting can be run in n log n. Some of the binary search, if you're doing a crossing in elements, that will also be n log n. And then lastly, there are basically a bunch of these functions that can take up much more time than that. So if you have like a nested loop, and each like the kind of context, the coding block in each loop does like O of n runtime. This could be expressed as O of n square. And there's also a bunch more that could take much longer than that, which as we have kind of seen what's like a lesson on recursion and this factorial function. If you don't like memorize it, the kind of like these like intermediate results that could really explode in terms of computation time. So yeah, really recommend reviewing this like kind of like a cheat sheet of big O runtime and just understand, okay, what are the operations? What are basically runtime of like my operation that I'm doing against my data structures? Or what is like the runtime of my algorithm? And you also have to be able to like evaluate this as like an overall, so then you can like actually come down with like the ultimate or the final runtime in space complexity for the algorithm. All right, so that was the lesson on the space and time and space complexity. Second topic is the technical question approach. This is also a really important point that we want to kind of keep highlighting, which is, when we get asked questions, we get really excited. And there's also part of us that may kind of want to jump onto coding right away and start trying to get the answers. But it's important to just take a pause and try to follow this like 5-step so then you can so that you can answer the questions in a really focused in a really focused manner. So the first step is to ask questions. Oftentimes, questions can be asked in a very ambiguous manners. So it's important to just ask if there's any kind of confusing part or if there are any parts that need clarification so that you can kind of narrow down the scope of your problem. Yeah, one example that we had was that during this kind of like interview to our Techquitable program, everybody was asked this question about, okay, find the oldest person from this input. But there are also a bunch of these questions that we could have asked with regards to like, okay, what is a data format? Can there be like a multiple people associated, with the same age or with the same name and so on. So it's really important to ask those questions and get clarified. And once you do that, you can then move on to designing an algorithm. The first thing you may want to do is to identify the brute force solution. And this is because you want to kind of like, come to like the just trying to come up with the easiest answer to answering the question, which oftentimes is like a brute force solution. And then from there, you can start like optimizing like the different data structures or different ways in which your code is run to start like optimizing or to reducing the runtime and the space complexity. So that's why you want to start off with like a brute force solution. And once you can identify that, then you kind of think about, okay, these improvements. And you want to kind of share this kind of thought process with the interviewer so that you can be on the same page about it and agreeing on like this proposed solution. And then once you do that, step 3 is to write pseudocode. You can just write pseudocodes or even use comments to just think about how you're going to write this code. This can help to kind of structure your thoughts before you actually move on to the implementation. And then step 4 is like writing code or actual implementation of the code. And hopefully here you're very familiar with your programming language of choice, so then you can write these codes swiftly. And lastly, this is the last step, which is once you have code, you want to test code and fix any mistakes, right? So to do that, you can try running your code against test inputs. And if your code test fails, do not panic. A lot of times, you could have a lot of typos in your code as you're writing fast. Or you could have some like edge cases that you have forgot to handle. So those cases could come up, but just try to like read the stack trace or the error messages that your compiler is telling you, and try to fix those issues one by one. And once you see that your code is running differently, then you can try to write more test cases to make sure or to gain confidence in your solution being right. So yeah, so these are the 5 steps that you want to kind of take in approaching a coding question. It's really important, so that's why we want to keep highlighting it for you guys. Okay, so now that we have talked about time and space complexity, as well as like the 5-step approach to technical questions, let's dig into the data structures. So the first data structure that we learned was array. So what is an array? So array is a simple data structure that represents a collection of items. And the items are stored in contiguous or neighboring block of memory. So you can imagine that each array could have these indexes that could point to an actual value. Yeah, so you could imagine using this a lot from your coding exercises. And these are the operations that we recommend knowing, which is that they're like basically these 10 operations that we recommend, which is like instantiating them, getting an element, inserting an element into array, deleting an element, and then number 5 is like getting the size of the array. And number 6 is like knowing how to like iterate through them. The simplest thing to do here would be to like just initialize your index and also manage that index yourself. But different programming languages have different ways, or even like multiple ways to allows you to iterate. So you may want to know all those like approaches, because some approaches would be more useful than the other in certain cases. There are also some mathematical operations such as min, max, and sum. And then there's also sorting that allows that you can also call against your array input, which depending on some, there's like an in-place sorting, or there's a sorting that would just create a new copy of this array for you. And number 9 is slicing, which is getting like a subset of your array from like a certain index to the other index. This is helpful to know when you also want to just get like a certain section of the input and work against that. And then lastly, just reversing the order of it of the elements in the array. So make sure you know how to do these operations in the programming language of your choice, because it will come up a lot in your coding exercise. Let's see. Yep, and then one problem that we went over is pivot index, which basically says, yeah, given an array of integers num, write a method that returns the pivot index. And pivot index here is the index where the sum of all the numbers to the left is equal to all the numbers to the right of this index, right? Hope this was like a practice problem that you got to work on, but it doesn't hurt to just try it again to see if you can actually solve it better or even faster this time around. Let's see, just to take a pause here, but any questions that we have on this topic? Okay, let's see, seems like I may want to turn off my video here because my signal is not that great. So okay, I'm also gonna move my location here to try to pick up better signal. Let's see, can you guys all hear me?
Can hear you fine. One.
Okay, and then let's see, seems like my screen share just went away, so let me bring it back up. All right, so to move on, so the second data structure that we went over is string. So what is string? Well, string is actually very similar to array, but each element is now made up of characters. So example here, we have this string that's called like weighty, right? But now like each index is pointed to each character. So it's very similar to array, but there are also basically other sets of operations that are very unique to string. For example, with strings, you may want to compare different strings together. You may want to also like join them or split them apart. So yeah, so there's a lot of similarity with array, but there are also certain operations that are very unique to string. And one example problem that we went over is palindrome. So palindrome, for context, is a string that reads the same when there's reverse. So example here is like some words like level, rotor, and stats. And basically you want to be able to like implement a function that checks whether there's a given string is a palindrome. And we went over a couple of techniques that can allow you to do that. One such technique is two-pointer technique, which is you want to iterate the string basically from two ends to the middle. So you have a pointer that starts from the beginning of the array or the string, and then another pointer that starts at the end. And you basically want to like move one of them at a time to compare if those like letters are the same. And once again, this is a really helpful technique that you may be also be able to use in other problems. Just being able to like work with pointers in general is like a really good thing to know. So yeah, so keep in mind about this technique that you have learned through this lesson of string. All right, and after string, the third data structure that we went over is stacks. So what is stack? Well, stack is a linear data structure that represents a collection of items. And it has a very special property called last in, first out, and it's abbreviated as LIFO. So analogies that we have in real life is things like stack of plates in cafeteria, where the first plate that you put on the top of the stack will also be like the first plate that you also get out when you take it out from this stack of plates. And you can also see in like other things that you use, for example, your browser, right? Your browser keeps track of all the history of pages you have visited. And when you hit the back button, it kind of magically takes you back to this previous page you have visited. And then, so in the back end, one implementation is that they could be using a data structure like stack to kind of keep this like LIFO or last in first out property or order. So then you can navigate back and forth with your pages. And these are the main operation that you should know, which is pushing an item, which is adding an item to the top of the stack, and a popping item, which is removing an item from the top of the stack. And there are also some operation that does not necessarily modify the elements in the data structure, such as peeking or like calling a top, which returns the top element without removing it. And there are other operations such as like finding the length of the stack, as well as like checking whether the stack is empty or not. So we also kind of like use this data structure in order to solve a problem called the valid parenthesis. Basically, the problem is asked us to determine if a string containing just the following character is valid. So basically string is valid if open bracket is closed with the same type of brackets. And then they also have to be closed in the correct order, right? So then hopefully this also became one of your practice problems, but one strategy that we used was like, for like opening brackets, just like, pushing into the stack. And then for like those closing bracket, we basically popped it out. And in the end, we checked if there's like any kind of remaining elements. If there were like remaining elements, then we determined that it was invalid. And if it was completely empty, then we kind of said that, yes, we did have a valid set of valid parentheses. And now the fourth data structure is what we call kind of the cousin or sibling of stacks, which is queues. So queues is also very similar. It's once again, it's a collection of items, but instead of having this LIFO property, it has the first in, first out, or what we call the FIFO property. So real world analogies includes like the lines at the cafeteria or like the printer queue, in which like the first person or first things to kind of go into this queue would also be the first person to kind of get out of it. And once again, these are the operations that you should know, which are push, pop, peek, size, and empty. What's very similar to the interface against the stack data structure. And this is also the data structure that you may have used when we learned about kind of like a graph algorithm such as like best first search, where queue is really useful in terms of like maintaining, okay, what is the order of nodes that I should visit? So really helpful data structure here. And the sample problem that we went over is implementing a queue using 2 stacks. So try it out if you haven't been able to try it, and see if you can actually try to implement this queue out of like 2 stacks that you also given. All right, moving on to the 5th data structure, we have linked list. Basically, how linked list is different from arrays is that it basically allows us to like dynamically link different elements together, instead of like in arrays where all these elements are placed in a contiguous like block of memories, and they're all in the same area. So this is really helpful when you want to kind of like dynamically like change the orders of things or like remove things, because you can do this with like almost like a minimum like changes in the memory. So basically, you wanted to kind of like know where the linked list is. You want to keep like a head element that points to the first element. And for the last element, you also want to make sure that it doesn't point to anything. So then you could also tell your code that the linked list ends here. And then this is an interface that we went over, which is that there's a class object called node that could have data. And it could also have the next pointer that could be pointing to the next element in the linked list. And then the operations that you want to know is things like head and tail. If you have a doubly linked list, in addition to the next pointer, you would also have a previous pointer. And there are also a bunch of other ones, such as like finding a linked list, searching an item in a linked list,
And then also things like inserting and deleting as well. Let's see. Sorry, just to take a pause here. Can folks hear me?
Yeah.
Okay.
Yeah.
Sorry, my headphone just kind of had a bad connection, so I'm gonna just have to change my microphone here. All right, so that's good to know. Yep, so as I kind of previously spoke, yeah, different type of linked list includes things like doubly linked list, which is like a linked list where you have both like the next reference pointer in addition to like, sorry, the previous pointer in addition to the next pointer. And then there's also a circular linked list, which is this like linked list where it also like takes it to the head of it also points it back to the head of the linked list. So then it basically allows you to have like this like a circular shape to your linked list. And the problem that we went over is this problem called reversing a linked list. So yeah, it's just a really good problem in, like to go over. You wanted to like really like figure out how comfortable you are with like what's like operating with this data structure. So the problem is pretty simple, which is giving the head to a linked list. You want to be able to reverse a linked list. All right, so once we went over this these data structures, we then learned about this technique called recursion. So what is recursion? Well, at the basis, recursion is a function that calls itself. Super simple, right? So what are the cases in which like this is helpful? Well, one example that we saw was with this example of factorial. So for context, factorial is like this mathematical expression where if you're given like a number, you would just like multiply it, that number against like any of the previous number in that sequence, all the way down to 1. So yeah, so one way to do that is to like kind of like use like a recursive function to answer or to solve this problem. But then there's one important thing about recursion, which is that you need to have base cases, because otherwise you would just keep calling it infinitely without knowing when would be like would be a good place to stop. So in this example with factorial, we said that the base cases here would be when the input number is 0, 1, in which case we want to just return 1. Otherwise, we want to just keep this recursive function and multiply whatever number that we're given with the output that comes from like the other recursive call, but the input to the other recursive call being a number that's less than 1 from the input number itself. So yeah, so in the code, this will be like how you might want to write it, which is like you have the base case here. And sorry, this example is now kind of talking about Fibonacci number, which is like a different mathematical like expression. But in this case, like it basically adds a number, the two previous number together in order to get the current term. So this is like how you could write it. And yeah, one other sample problem that we went over is this problem called symmetric tree, which is that given a binary tree, you want to check whether a tree is symmetric. Symmetric here means that a tree is like a mirror of itself. So you could basically call like a recursive function that basically in which like at each call it basically compares like a value of one node against the corresponding value, basically the corresponding node's value in part of the same tree. And if they were to be different, then you know that you don't have like this like symmetric tree. And if they are equal in all places, then you know that's how you know that you have a symmetric tree. So yeah, these are the kind of problems in which like recursive function is really helpful. And later on, we also kind of like learn other algorithms, things like depth first search, which is like also in which recursive function could also be used in order to implement for its implementation. All right. So then once we went over recursion, we then went over this technique of sorting. We learned about 3 different types of sorting. The first type was called bubble sort. which is kind of like the most basic type of sorting that can be run in O(n) squared time. And then we learned about selection sort, which is a slight improvement compared to bubble sort in terms of how it compares like different numbers in order to like get the sorted array. But this is like how, yeah, but then we also learned that in fact, this actually still have like runtime of O(n) squared, so it's still not like an optimal sorting. And then lastly, in terms of like a third sorting algorithm that we learned was called merge sort. This sorting algorithm basically uses this principle called divide and conquer method. So we basically split the subarray into halves until they're in the subarray of length 1. And once we kind of split it all the way down, in which each subarray has a length of 1, then we kind of build them back up in the right sorted order by comparing each element and creating this like new array that basically takes elements in the sorted order. And this merge sort has the best runtime in terms of sorting algorithm, since in most cases, a lot of sorting algorithms have a runtime of O(n) squared, but with merge sort, you have a runtime of O(n) log n. So mostly when you're working with like sorting, you don't really need to kind of implement sorting from scratch because most like languages just provide you with like the sorting algorithm. But then you can kind of like, use assumption that, okay, this sorting function is running in O of like n log n. And then once we finish sorting, then we learn about this another technique called searching, which is like a searching an element in a given element. So the first type that we learned was this search called linear search, which is very simple. You basically run like a for loop against like this like input and see if the input contains the element that you're looking for. And as you could imagine, the runtime of this has O of n, because in the worst case, that element that you're looking for shows up as like a last element, or it doesn't show up at all. So you have to like scan or reference against like all the elements in this input. Yeah, which could be time consuming, especially if your input is big. This is why we also learned about the other type of search, which is binary search. So binary search basically assumes that your input is given in a sorted order. But once we know that the input is in a sorted order, they're basically clever things that we can do to like navigate our search and cut down our search time. So binary search, essentially what it does is it goes to the middle of the input and see if the element that we're looking for is greater than the element that we have or smaller than the element that we have. And depending on whether it's greater or less, we basically choose which direction to go, which sub half of the array to kind of focus on. And we keep doing that until the middle element that we're looking at finally equals to the element that we're looking for, or basically we just like come down to this like subarray of like length of 1, and we realize that this input doesn't contain the element that we're looking for, in which case we just end our search. But with binary search, this search can be done in O of log n, which is faster than the linear search, which has the runtime of O of n. And the example problem that we went over is this like sparse search problem, which basically says, given a sorted array of strings, which is interspersed with empty string, we want to write a method to find a location of a given string, right? So example here that we have is we have a string with all these names of the fruit that are sorted in alphabetical order. And maybe it's like, we want to see if this input array contains like the fruit that we really want to be looking for. For example, maybe we're looking for the fruit grapes. Yeah, I mean, the fastest, maybe like the most easiest way to do it would be to do a linear search. But since this array is already sorted, then we could basically use binary search to cut down the runtime. But then the kind of trick here is that this input is also interspersed with empty strings. So you also have to kind of modify your vanilla binary search with a handle or with like kind of helper to kind of like address those empty strings. So yeah, it's another good practice problem that we went over during class. All right, and then now we're kind of moving toward the end of our programs like topics, but Right. So this was like data structure that we just learned last week, which is trees. So what is tree? Well, the tree is a data structure that is used to simulate a hierarchical tree structure. And we also learned about different types of tree, which includes binary tree, binary search tree, n-ary tree, which is just a generic form of tree. And then we also have tree, as in like TRIE, which is really helpful for things like spelling checker or like autocomplete. So in code, we can represent it as like these classes. It's very similar to the node that may show up in things like linked list. However, in contrast to linked list having like a previous or like next pointers, what the tree has is this element called children, which can basically contain references to the nodes that it's associated with. And in terms of binary tree, that children references is now further specified into like the left and right pointers, because it also because binary tree only has at most 2 children that's associated with each node, and it has the direction of right and left. Yep, and then we also talked about, okay, what's special about binary tree, which is that binary tree could be really useful in the context of a binary search tree, well, for searching. And it could also be helpful in terms of like ordering things. So using in a data structure such as heaps or priority queues. And then we also went over like traversal types, in which there are 4. So at the top level, there's like breadth first search and depth first search. What's breadth first search? There's like a level order traversal. And then what's depth first search? There's like pre-order, in order, and post-order traversal. So yeah, what this says is basically there's like a slight differences in the order of the nodes in which this algorithm or this traversal type would visit. So with breadth first search, you can imagine that it basically visits all the nodes in like the same level, like what's like a level at a time. Whereas with depth first search, you basically try to go down as deep as you can in like this one path that you choose to go. And once you can no longer go down anymore, you basically move back up to just like other nodes, to the previous nodes that have like reference to the other nodes, and then go down that path, and then basically keep repeating the same process. And then once we learned about trees, we then learned about graphs. So with graphs, this is really helpful to kind of represent connection between data. And it's used in problems like shortest path and network problems. So one of my favorite problems is use of data structure of graph is to represent something like a social network. Like I could basically represent each person in my social or friends network as a node. And if I do really have like a friendship with them, then that could be represented as the edge. So yeah, so it could be used to represent this kind of like a network like data structures. And let's see. And we also learned about different terminology, which is like these things like nodes, or the other name that we called it is vertices. And then each vertex or node also has like these edges coming out. And these edges could be directed or undirected. Directed means they would have just have a direction. And then lastly, some graphs could also have cycles, especially if they're directed, but then they could basically end up in a path where you can just keep repeating, keep like visiting the same like cycles or path. So with code representation, there are 2 main ways to do it. One way is to represent it as like an adjacency list, which is basically saying that basically each vertex has a list of its neighbors that it's connected to. So yeah, so you could basically have like this array that could basically say, hey, like these sort of nodes that this node is connected to. And then and then the other way in which you can represent it is using this thing called adjacency matrix. It's basically like a 2-dimensional data structures in which basically like a pair of like the nodes could be represented as like this cell in this matrix. And when they do have like a node, if they do have like a path or edge that are connecting them, then that cell could be like represented as a true. And if not, it would be just represented as false. And graphs could basically have like these algorithms such as depth first search and breadth first search being run against it. And the runtime of these algorithms is the same, which is like O of B plus E. This is different from like, all the other runtimes that we have been kind of representing with relation to the input. Because like, okay, V here is the number of vertices and E is the number of edges, right? And in terms of implementation, we could use both recursive or iterative. And yeah, and then lastly, BFS. This is like one kind of example of implementation using an iterative method. And you can see that BFS uses a data structure of Q to maintain the order of nodes in which it wants to visit. And similar thing is happening with depth first search. This is also the iterative implementation, but instead of using a queue, it's using a stack to manage the order of the nodes in which the DFS should visit. And the kind of example problem that we also went over in class is this problem called number of islands, which is that given like a 2D matrix, you want to find a number of islands. And basically the island is defined as like a group of connected ones in this matrix. And here you could use like a BFS or DFS, depending on how you look at it to just count, how many of these are islands in this matrix. Alrighty, well, that covers all the technical topics, and we have about 10 minutes left. So might have to kind of like rush through this like non-technical topics, but just to take a pause here, but do we have any questions about the technical section?
No question.
All right.
Should we always try to implement the most efficient solution we can think of, even though it's harder to implement? Or what if we don't finish that implementation? Should we just try to do the brute force first?
Yeah, that's a good question. Because as you can imagine in an interview, you're in a very like a time pressured environment, right? Oftentimes you're given 60 minutes, but even with that 60 minutes, like the first 5-10 minutes could be used on introduction. So you're really left with like anywhere from like 40 to 50 minutes to kind of like answer your question. So that's why what we recommend is like just communicating out the solutions first with your interviewer, right? So before writing any code, you should be able to kind of just establish the brute force solution, and then see if you can like try to optimize it, right? And then see there's like a way in which you can introduce like another data structures to cut down the runtime. Or there are any ways in which you can like change the orders in which like you visit things, or even use like techniques that we have like learned about, such as like binary search or sorting, to see if you can like just cut down all those things. But all that conversation should be kind of happening before you write any code. Because like, let's say that in the best case scenario, like, you establish your brute force solution and you also come up with like a proposed solution for optimal solution. And then you can also implement it, right? That would be like a really strong, like a performance to have during the interviews. But let's say that during implementation, like you get stuck on like this, like really specific parts of it, in which case, like, okay, you did not finish. But at least, just by having that conversation up front, the interviewer would know, hey, actually this person, would have been able to finish, had they, been able to kind of figure out this like last part, or, had they been given like a few more minutes. So even though it might not be like a perfect performance, then they will kind of still take that into account, right? So yeah, that's why like, our kind of like recommendation has been to kind of like, just have this conversation first and then move on to the implementation. And even if you can't like come up with an optimal solution, then that's fine. Your interviewer might just ask you, just implement this brute force solution that you have, and they will still try to gauge your coding ability. and that might actually still do the job. So, yeah, so does that answer your question?
Yeah, that makes sense. Thank you.
Alrighty. Right. So yeah, let's just like wrap up this presentation with the non-technical topics that we kind of went over. So in terms of interview process, so you kind of learned this is a roadmap, which is, trying to interview for software engineering job is not like a short-term process, right? It's pretty much like a long-term process that kind of starts out with you deciding like learn computer science or software engineering or any related sets of courses in school, right? But once you do that, there's like a short-term preparation, which is the period of time in which you want to review all the data structures and algorithms that you have like learned in your class. And you also want to like practice, using websites such as using the websites such as LeetCode or like using the books such as Cracking the Coding Interview. So then you can be kind of used to the format or like that a lot of these tech companies ask these questions in. And once you feel comfortable answering these questions, then it's time to like start applying to jobs, right? Like you want to like think about, okay, what are the jobs that I would like to like apply for? And then start this process. And once you start this process, hopefully you'll get some calls from like these recruiters. And once you have like some conversation and they go well, then you'll basically kind of be looped into like this like technical rounds of interviews. And hopefully everything goes smoothly. So then you will eventually like lead to a job offer that you can kind of consider whether to take and just spend the next, whatever many years of life, like learning your craft and working in this job. And with the interview rounds, what would happen is once you apply with your resume or cover letters, you basically have like a resume screen that a lot of these companies like, do with these recruiters or these like, HR softwares. And once you're selected, you have this call, like usually a 30-minute call with the real recruiter, just like, going over your background and explaining about your interest in the job. And also this is a chance for you to learn about, okay, what does the job entail and what is your responsibilities going to be like? And once that happens, then you're like starting to like these like technical rounds where each round is like usually structured with like a 60 minutes and you'll be basically, answering and implementing these questions, over a phone call or a video call. And once that happens, once few rounds of that happen, then you have like an on-site, which is remote, in the kind of current pandemic environment that we're all in, which is like a kind of like a series of session in which you basically do like in which you basically repeat this kind of process, and hopefully that basically like leads you to like a place where like the interview committee kind of consider your candidacy and decide whether they want to extend a job offer or not. And just to kind of go deeper down, what happens in each technical round. Once again, the first 5 to 10 minutes is like spent on introduction. And then the next 40 to 50 minutes is like spent on problem solving. And then the last 5 minutes like spent on like Q&A. And these are the interview rubrics that a lot of these companies use. This is not like a one standard that all companies use, but these are just common themes. So yeah, some of these aspects include things like problem solving, which ask kind of like, whether this person was able to answer this question in time on how optimal their solution was. Then there was like, another aspect around technical knowledge, which is like, does this person, were they able to implement without any bugs, or, how was the coding style of this person? And the third aspect is the communication, which is how was this person able to communicate with the interviewer? And are there signs like that says that this person will be able to collaborate well with like other teammates? And lastly, there's also another aspect around experience, which is like the ability to learn, which is, and this kind of like things can come up, us like the interviewers like kind of give you hints about, problems that you may be kind of struggling to answer, or do some other conversation about like your previous experience in your classroom or like other internship experience. So yeah, good to keep in mind that, these are often the things that your interviewer will look for. So you obviously want to present yourself in the best light, and just, yeah, and see if you can do well in each of these aspects. And lastly, how can I best prepare? Well, these are like 6 main tips that we have for you, which is, one, you want to prepare a great resume. And you also want to study data structures and algorithms, starting with like, whatever slides or maybe videos that we have kind of shared with you. And there are many other resources out there, which we are going to also point it out later in this presentation. And you also have to know your big O, or just analyzing your runtimes and space complexity. And then the 4th tip is that you also want to like just have like repeated practice with solving these kind of problems. And the 5th aspect is that you also want to practice sharing out loud your thought process, because honestly, a big part of these interviews is like a communication with your interviewer. And lastly, to kind of like simulate that kind of environment in like the most closest way, you might want to do a mock interviews with your friends or mentors, so that you can kind of simulate that environment. And to dig a little deeper into resume, I hope everyone had a chance to kind of create their resume. But once again, these are the tips that we have. And we do have a resume template that you can kind of like work, that you can like build your resume off from. So you can just click on this link and it will just take you to this Google Doc. So you can make a copy of it and start filling out this like template based, with your own information and experiences. And lastly, the behavioral questions. These are the questions that interviewers like to ask in order to get a feel for like what your personality is and to understand your background a little bit more. So these kind of questions often start with like questions like, hey, tell me about a time when you did this, or like, what do you do when you face a problem, or like, have you ever like basically, basically experienced like this specific situation. And interviewers just try to ask you some of these questions in ways that will like really, make you think about your past experiences or past, moments, and see, how you reacted or how you behaved during those times. So the strategies you can of course prepare in advance, which is you want to pick the right story, and you also want to make a statement. What is about this story that that highlights like some of my strengths or weaknesses. And obviously, like you also want to be able to finish strong so that you can like leave like a lasting impression on these interviewers. The things that you could do to kind of prepare this is that we have this thing called story grid, which is like this kind of a template of notes that you can fill out to see, okay, what are different things that you learned in, through like a different project or experiences. There's also another technique called STAR method, which stands for situation, task, action, result. So you can also follow this like pattern and try to like, describe your story in this manner. And lastly, your interview session often ends with like a Q&A session that gives opportunity to ask an interviewer. So yeah, oftentimes like, you don't want to just ask, hey, like you don't want to just say, I don't have any questions, right? You always want to like, express interest and also try to learn more about the job. So these are different categories of questions you could ask. So yeah, so we also recommend thinking through about that and yeah, try to kind of prepare some questions in advance. All right, so that also wraps the non-technical topics that we have also went over in Techquitable. Before we head off, these are additional resources that we want to impart with you. So first of all, with Techquitable, these lesson slides and recorded lessons are always going to be available to you for free through just like Google Drive link, as well as like this YouTube channel that we have. So yeah, feel free to use it anytime, and also even share with your friends and classmates if you think this will also be helpful to you. This is all public to everyone. And then there are also books like things like Cracking the Coding Interview or Elements of Programming Interview that would also allow you to get access to more questions and also allow you to like think about like, approaching certain questions in a better way. So all these kind of like books can be bought on Amazon or any other bookstore. So if you're the type of like a person who like learns the most from reading a book, then I will highly recommend looking into those options. Then there are also categories of resources available through websites. Code Academy has like a good resources on like helping you to learn about like a language. So if you are like still, you want to brush up on the language of your choice, such as like Java, C++, or Python, Code Academy could help you do that. And there are also a bunch of other websites such as Educated, Exponent, and Recode that are like more focused on like interview preparation. And allows you to do that in like more interactive format. So yeah, so these are good things, so good websites to visit as you kind of like also go off on your own to prepare for these interviews. And lastly, if you think you also want to kind of keep like, looking for this kind of like a structured format or mentorship or help, there are also a bunch of other nonprofits that you could also turn your focus into. ColorStack is like is a nonprofit that is also dedicated to helping African American and Latinx students get into the tech industry. Women Who Code, sorry, there's a typo there, is a nonprofit that helps basically females like do better in the tech industry. So if you have female students, this might be an organization you may want to look into. And lastly, if you're based in New York, there's also a wonderful program called Pursuit that allows you to basically like learn more about programming through like a boot camp format. So this might be something you want to also look into if you feel like, well, if you feel like you want to continue on with your coding or software engineering instruction of study at college. And to wrap it up, so yeah, so honestly, thank you guys so much for sticking with us through the last like 10 weeks. I hope this was like a transformative experience and you got to like learn something new by attending these like lessons and your mentor sessions. And before we end this program, there are just these tasks that we'd like to ask you to do. One is to attend the final week of mentor sessions with your mentors. So you have like 1 or 2 lessons left, like, highly recommend making the most use out of it. And just like, just to get this more like individualized help through those format. And yeah, if you also have friends or classmates who you think would really benefit from a program like Techquitable, we'll really appreciate it if you could like refer them to us, and we'll be very happy to work with them for upcoming full cohort. So yeah, we'll really like to ask you for help here. And the third action item is that we'll also be sending out an access survey. It's going to be very similar to the midterm survey that we sent out, but we would really appreciate if you could spend 10 or 15 minutes of your time filling it up and leaving feedback. As we really appreciate, we would like really look closely at them and try to learn from them and make our program even better for everyone. And the fourth one is that keep us up posted on your job and internship status. Like, if you got a job or internship offer, that's great. Really makes us happy to like hear that maybe some of the help has like led to some of these offers. And on the other hand, even if you're not finding success in finding a job or internship, we really want to do our best as a community to see if we can like really help you, further help you in this in this process. So just let us know. Just email us or Slack us about your status, and and we really appreciate those updates. And lastly, you have a lifetime access to a Slack group. So yeah, feel free to stay engaged with our community, and just drop in and say hi, or maybe as you kind of grow up to become a full-time software engineer. We also really appreciate it. You could also come back and revisit our program and also offer help to others. So yeah, this is the one final ask that we have for you. And with that, once again, thank you very much. And we hope the best of luck for your for your upcoming journey.
Thank you.
All right, what's that? We'll just wrap up the lesson. So, yep. See you guys all.
Thank you.